To understand how modern businesses use AI, you need to understand Retrieval Augmented Generation, or RAG. This architecture functions as a dedicated search engine, providing the AI with a direct connection to a company's private internal data. This chart shows 2024 enterprise adoption rates for AI architectures based on Menlo Ventures data. Within a single year, the number of enterprise deployments using this method jumped from 1/3 to 1/2. RAG became the industry standard because it addresses a significant limitation. Large language models are limited by their training cutoff dates. By searching a live database, the AI can supplement its static memory with fresh, relevant facts. Imagine a compliance officer at a large bank. They ask their internal AI a high-stakes question. Does a specific corporate transaction require regulatory approval? The system provides a beautifully formatted, highly confident answer. It is also completely wrong. A moment of realization. This error did not stem from the AI making things up or inventing details. The system followed its instructions and processed the information it was given. The problem lay entirely in the documents it was using as a foundation. The search engine had pulled a superseded, completely outdated version of the corporate policy. Because that old document was the only evidence provided, the AI based its entire answer on retired rules. By connecting a search engine to an AI, organizations shift the risk of error from the model's training memory to the system's retrieval process. The core challenge of ensuring the AI has the right facts has been relocated, not resolved. Under the hood, this pipeline operates like a strict multi-step assembly line. Each component has a specialized isolated role, and they do not overlap. This standard RAG pipeline has 4 steps: query, search, context window, and generate. The generation stage produces no original thoughts. It only synthesizes the specific evidence the search stage places directly in front of it. To see the specific research on how these component failures interact and amplify each other, you can read Garrett Phil Bauman's full article on Medium, linked in the description. This separation means that even the most advanced generation model is entirely at the mercy of the retrieval system's accuracy. The structural flaw in these pipelines comes down to a matter of definitions. Retrieval engines are programmed to find documents that are mathematically similar to a prompt, while business users need documents that are relevant. To a machine, similarity means shared vocabulary and conceptual framing. If the words overlap, the documents match. But relevance requires precision, exact versions, and temporal authority. A retriever struggles to distinguish a current policy from a superseded one because their language is nearly identical. This divergence between mathematical similarity and practical relevance happens constantly, regardless of how advanced the retrieval software happens to be. Any system built purely on mathematical similarity will struggle when tasked with the strict precision required for operational, regulatory, or legal work. The outdated compliance policy is a perfect example of a near-miss document. It is structurally similar enough to be easily found, but factually incorrect for the current situation. This is more hazardous than a total retrieval failure. If the search engine returns completely unrelated files, a well-tuned AI will simply and safely reply that it doesn't know the answer. However, a near-miss document gives the generation model everything it needs to be persuasive. It provides the exact corporate tone, terminology, and formatting required to construct a highly convincing false answer. In a high-stakes enterprise environment, an AI that confidently cites a near-miss document creates far more risk than an AI that simply fails to answer. Humans instinctively judge an AI system based on the quality of its final response, how well it's written, and how accurate it appears on the surface. This creates a measurement trap. When the final text looks perfect, any error caused by the underlying retrieval layer becomes entirely invisible to the user. When the output is wrong, organizations often waste resources trying to upgrade the language model, assuming the brain of the AI is the problem. Upgrading the generator is ineffective if the foundation is flawed. A more powerful model will simply write more sophisticated lies if the retriever continues feeding it the wrong facts. The RAG architecture guarantees that generation is supported by retrieval, but it cannot guarantee that the retrieved information is what the user actually needs. If an AI provides a wrong answer, the first step is to stop scrutinizing the final generated text. You must look backward in the pipeline and verify if the correct answer was even present in the initial set of retrieved documents before attempting any technical fixes. In Episode 4, we will look under the hood at the geometry of embeddings to see exactly how machines calculate similarity. Until then, you can dive deeper by reading the full article on Medium. The challenge of AI reliability has shifted into the realm of search engineering. We are finding that what an AI knows depends almost entirely on the precision of the facts we hand it.